My name is Jim. Welcome to part 3. What I'm going to be doing is talking about the applications of DC circuits. And DC has the characteristic of being kind of dry. Is where you get into the applications. I think you can see a little bit better that it's truly useful information. And what we're going to do is start with a relatively complicated device called an N-channel metal oxide semiconductor field effect transistor, and this is the workhorse for DC switching, and it does have a big brother which I won't speak to. Its operation is very simple. If I take the smallest of batteries, maybe a 12-volt garage door opener battery or a 9-volt transistor radio battery, and make the gate positive with respect to the source, I turn this device on and hundreds of amperes can flow through this. So by a simple little voltage here, which is insulated from the channel, that little black mark shouldn't be there, but it is, I can switch huge amounts of current. And like an NPN transistor, it uses the same symbol with regard to the direction of the arrow. Conventional current is flowing with the arrow. Now this is an abbreviated symbol. The real industry symbol is quite complicated and further confused by the body diode that's inside of it, so this is what most books use and this is what I'm going to use. It also has a complementary cousin called a P-channel that works exactly opposite. In this case, if the gate is made negative with respect to the source, the device turns on, and once again the arrow shows the direction of conventional current flow. So if we go to analyze this, and we're only interested in two states, completely on and completely off, because these are the most efficient. That is, the device dissipates the least amount of power. So we'll start by looking at this transistor when it's totally turned on, and it has this very nice characteristic that it looks like a resistor. It's not really, it's embedded in the silicon, but it looks like a resistor, and the name of that, it's an R, is RDS on, standing for resistance drain to source on, and we're going to let this be approximately 0.8 ohms. So if I'm going to analyze this circuit, which has a 10-volt battery and a 9-volt load, I'm kind of confused by this symbol of the transistor, so what I'm going to do is represent that with its equivalent circuit when it's turned on. And as you can see, that kind of breaks down into a very simple voltage divider system, current flowing in this direction. And if I want to know parameters about the circuit, like V out, remembering that this is a doubly subscripted variable, the second subscript is ground in this case, so the black lead of your meter will go here, and the red lead for V out would be here. And we can find this by using voltage divider once again. So V out would be 10 volts, our source voltage, times RDS on, 0.8 ohms, divided by the total resistance, which would be 9.8 ohms, and that means gives us a V out of 816 millivolts. Likewise, if I wanted to find the voltage across the 9 ohm load resistor in this example, what I've elected to do instead of voltage divider is to take 10 volts, subtract from it 816 millivolts, which gives us 9.8 volts across the load. So the reason I can do this is because of Kirchhoff's voltage laws. The drop on this side has to be equal to the rise on this side. So analyzing the power in this guy, if I want to know how much power the FET's going to dissipate, and the reason I got to know that is it's easy to overheat them. They're small devices. And if it's too much, what I'm going to have to do is put a heat sink on it to help get rid of the heat. So to find the power, I elected to use V squared over R, and that comes out to be 832 milliwatts. I will probably need a heat sink on a standard TO220 case. Likewise, the power in the load would be its voltage squared divided by the resistance, 9.18 volts, and that gives us 7.43 watts. Now what to keep in mind when we talk about power is if we have a 1/2 ohm resistor and that's dissipating 1/2 watt, we can barely put our finger on it. So that's an idea. The larger the body is, the physical area, the cooler it in fact becomes because there's more radiating surface. So this is the way you would handle a FET DC switch, is by decomposing it into its equivalent series circuit. And this could be high side too. This could be RL, and you treat this the same way. You have to be told what RDS on is for this part, and that's fully turned on. Now let's take a look at the other case, and that's going to be when the FET is turned off. Now I'm showing you a little box here I did before too, forgot to mention it. This is the controlling electronics. We're not really interested in that right now. So what we want to know, as before, is what is V out relative to ground, and what I also know is that this is a low side switch. So drawing the equivalent circuit of that, again I have a simple series circuit, and now for the off transistor I'm going to substitute in a switch which is open. So what I can say about that is, since the current flow is 0 amperes and the voltage across the 9 ohm resistor is 0 times 9 ohms, I'm going to have 0 volts. That is, the drop across the resistor is going to be 0 volts. Now, what I know is that this side of the resistor is connected to +10 relative to ground. And if the drop is 0 volts, what that means is V out is going to be 10 volts. Many students would say that the circuit's on because you have an output voltage. It's off. It's a low side switch. The power in the FET, well, before we figured that out when it was turned on, and it's approximately equal to 0 watts. I should have wrote down 0, but there's a teeny amount of leakage. So for all practical purposes it's 0, and the power across the load resistor would also be, for all practical purposes, 0 watts. So you can see we can take simple DC circuits and analyze rather complicated devices very easily by modeling them. So this circuit doesn't exist per se, because this off here is very involved with some physics inside the transistor, but it looks like an open switch. So you handle it as you would a standard simple series DC circuit. Thanks for listening.